Okay, so let us start our today's discussion on the MEMS sensor. Yesterday we have completed the complete overview or the process details of the MEMS technology, right? And just given the basic introduction of the MEMS sensors. And we told that we are firstly focusing on the mechanical type MEMS sensors, under which the accelerometer, pressure sensor, gyroscope, so those things will come into, right? So let us start our. So this one also we have just told that what are the typical microstructures we used for developing the MEMS mechanical sensor. So what we can see that here typically the cantilever beam is one type of structure. Then here we have the fixed beam configuration that we call as the bridge configuration, and here we have the diaphragm or the membrane, and these are the typical structures which we use to develop the MEMS mechanical sensor, right? And what we told that if we want to whatever be the physical quantity we want to save, that ultimately we have to convert it into the electrical output, which we can do either with the help of this piezo-resistive mechanisms or the capacitive mechanisms or the inductive mechanisms, right? Now here just for example we have talked about that if we consider the piezo-resistive case, then how it will look like. So here is the piezo-resistive measurement application has been shown here. So here what we can see that this is one typical cantilever beam where this end is the fixed end and this end is the free end where a proof mass has been attached, right? Now where we have to place the strain gauge of the piezoresistor, the location should be where the stress or strain development will be the maximum, right? So obviously if I consider a cantilever beam and then towards its fixed end or the anchored region, the stress or strain development will be maximum. So that's why the strain gauge or piezoresistors will be installing in this fixed end region, right? So whenever some force is applied on this cantilever structure, so then the strain gauge or the piezoresistor will experience the stress, accordingly its resistance will change, fine, and it can be again converted into electrical output with the help of some Wheatstone bridge type of circuits, right? And as you said that doped silicon resistors can be used to make this type of piezoresistors, right? In the next case, here we can see this capacitive measurement technique where this is again one cantilever structure, and here we can see suppose this is your cantilever and here we have the substrate or this bottom layer, and whenever some force is applied on the cantilever or the pressure, so then this particular beam will be deflecting and there will be a gap change between this beam as well as the fixed substrate, and this gap change can be calibrated in terms of the capacitance value, right? Because the capacitance is a function of the separation, that is the gap, area of overlap as well as the dielectric permittivity, right? So here just for the representative purpose we have shown you the example that if we consider piezo-resistive or capacitive type measurement techniques in case of development of pressure sensor, then how it will look like or how it will work, right? Is it okay or any doubts? So again I am saying that if you feel any sorts of doubts or clarifications, please feel free to ask anything, don't hesitate it, you can communicate either mail or Skype, whatever means, right? Or even if you want you can come to my office individually as well, right? Okay. So next let us focus on the MEMS pressure sensors. So that is the first sensors which we are going to discuss. Now as I said that pressure sensor, what is its job? If I tell that this is a pressure sensor, then the input will be the pressure and output will be the, obviously we will prefer to get it some sort of electrical output, right? And what are the ways or means by which we can convert the mechanical pressure into electrical output? So as I said just in the previous slides, either I can go for some piezo-resistive mechanism or capacitive mechanism. You can have other mechanisms as well, but here we are focusing on these two types, that is the resistive and the capacitive, fine. And so here in the left side you can see the schematic diagram for both the piezo-resistive and capacitive type, whereas in the right side you can see the actual that pressure sensors. So the top ones are some sort of macro scale, whereas the lower one, so this is the macro scale pressure sensor, whereas this one is the some sort of IC type pressure sensor, right? Now let us look at their working principle. So this is your piezo-resistive pressure sensors where what we have. So this already we have seen that this is your diaphragm, right? and this diaphragm, how we can manufacture it, that already we have discussed during the bulk micromachining process, right? And from this lower side the pressures will be applied and the diaphragm will be deflecting or vibrating depending on the applications of pressure, fine. And here we can see some sort of glass capping is there, that is for just for the some sort of packaging purpose, right? Now as you can see here we have the place the piezo-resistor, right? So whenever the pressures will be applied through the inlet, the diaphragm will be deflecting, and because of the deflections the piezo-resistors will experience the stress or strain, right? So accordingly its resistance will change, which we can connect it to some Wheatstone bridge circuit, and then we can basically this Wheatstone bridge that will give you directly the voltage output, right? So this is the basic mechanisms of the piezo-resistive type pressure sensor, where on the diaphragm we are depositing some sort of piezo-resistive layer, right? And if you remember that piezo-resistive, how we can generate, we can use the doped polysilicon, right? You remember? So that doped polysilicon that can act as the piezo-resistors, and they are of semiconductor type, and as we said that semiconductor type strain gauge or these piezo-resistive sensors or piezo-resistive materials, so they are having high gauge factor, and because of the high gauge factor their sensitivity is more, right? So here just for representation purpose that two strain gauge or piezo-resistors we have shown here. You can similarly use another two at the bottom sides as well, or to improve the sensitivity further, right? Now in the lower portion you can see the capacitive type pressure sensors, where obviously the pressure which we will be applying, that will be converted into electrical output by the capacitive transduction mechanism, right? So here what we can see that in this figure again, here we have the silicon diaphragm and the pressure is applied from the bottom side, and here what we will do on this diaphragm, this will act as one electrode, and on the top side we have one pyrex, and below that we have another electrodes. So basically when it will be deflecting, so then gap will be changing between the diaphragm and the upper side, and accordingly the capacitance value will change, right? So here basically we are using four typically capacitors. We can see that two are corresponding to the reference capacitor and the two are sensing capacitor. So that means the sensing capacitors will be placed where that because of this deflection these portions will be having the maximum deflection, and accordingly this gap will change, which will be acting as the sensing capacitor, whereas for making the bridge complete we can have the reference capacitor in the device itself, or we can use externally as well. So the basic point what I want to highlight is that in case of capacitive type, because of the applied pressure the diaphragm will be deflecting, and when the diaphragm will be deflecting, on the diaphragm we will coat or deposit some electrodes, and above that diaphragm also we have some frame where some fixed plates are there, and when the diaphragm will be vibrating or deflecting, so then this gap will change, accordingly the capacitance will change, and this capacitance again we can connect it to some bridge circuit which will give you the direct voltage output, right? So these are the just the basic overviews of the piezo-resistive type and capacitive type pressure sensors, and essentially you can understand that this type of pressure sensors are fabricated using the micromachining technology, right? So you remember that we have discussed that bulk micromachining technology, using which we can develop this type of membranes, which is the essential part of the pressure sensors, right? Is it okay, or any doubts? And the right side you can see that corresponding the actual how the sensors looks like, fine. So if it is okay, so let us go to the slide. So here where we have discussed in detail about the working principle of the piezo-resistive pressure sensors, fine. So you can see that this particular diagram also, you must remember we have shown you earlier in some another aspects during the fabrication process discussion, where this one is your silicon diaphragm and this yellow correspond to the basically that hard mass, right? And the red line correspond to the polysilicon resistor, which is acting as a piezo-resistors, and on top of that we have the aluminum metal, which is again used for taking out the connections, right? So this is just one representative or schematic view. Now in the bottom side we have shown, suppose if I have just for example here we have shown one that square type diaphragm where four piezo-resistors or the strain gauges are placed, right? So this is one type of views. This is another simplified view where you can see this is your that actual diaphragm, and here R1, R2, R3, R4, these are the 4 piezoresistors, right? So basically those 4 piezoresistors will be acting as the 4 strain gauge, which we will be connecting to the Wheatstone bridge circuit to convert the change in resistance into the change in voltage, right? Isn't it? So now what will happen basically, how these particular things will work. The basic principle already we have discussed, that if I apply some sort of pressure, so then the diaphragms will be deflecting, and because of the deflection the stress or strain that will change across this basically that piezoresistor elements, and its resistance will change depending on the stress or strain, or basically tensile stress, tensile force, or the compressive force. According to that, either resistance will increase or decrease, right? Now that particular, so we have discussed about that quarter bridge configuration, half bridge configuration, full bridge configuration. Remember during the discussion of the sensors. So those 4 piezoresistors we can connect it to the Wheatstone bridge to convert the change in resistance into voltage, and in that way the pressures will be finally converted into the voltage output, right? Now if you see carefully, the orientations of the piezoresistors, they play an important role. So here just for the simplified, you focus on this yellow diagram, right, where R1, R2, R3, R4, all of them are placed in this particular orientation. Now if you if you see that, suppose when the membrane will be bent downwards, then what will happen? The tensile, so basically that causing tensile force or stress on the membrane surface at the edges, right? The parallel resistors, listen carefully, the parallel resistors will be under lateral stress, and it will show a decrease in resistance, whereas the perpendicular ones will be in longitudinal stress and they will show an increase in the resistance. So what does it mean? You look at these 2 diagrams. So here what we have, this is your diaphragm, and this is the piezoresistor placed. Now when these particular things will be bented downwards, so suppose in the middle we are applying some force from the top side, and when it will be bending downwards, then these particular things will be elongated along its axis, and accordingly you can understand that its length will be increased and the resistance will essentially increase. Fine. Whereas if you look at the other one, so then what will happen? If you similarly here also in the middle, if you apply some force or pressure, so then this particular piezoresistors will be elongated along its width, and the length will be essentially reduced because the volume will be same. Fine. Accordingly, these piezoresistors will be stressed transversely and its resistance will be decreased. Fine. And these particular things we will be exploiting to basically that develop this piezoresistive type pressure sensors. Fine. So here you can see the corresponding diagram, that R1, R2, R3, R4. So basically 2 resistors will be, so suppose you understand that, suppose here we are applying the pressure at the middle portion, so then what will happen? This R1 and R3, they will be elongated along its length, so R1 and R3 resistance will increase, whereas the R2 and R4, they will be elongated along its width, so their resistance will be decreased, and this R1, R2, R3, R4, they will be connected to the Wheatstone bridge to convert the delta R into delta V, right? And delta R we have got because of the delta P. So in that way finally the delta P will be converted into the delta V, right? Now the second line, what we can see, that deflection in the diaphragm can be measured using the piezoresistive strain gauge located in the region of maximum strain. So we have to understand where we will place the strain gauge or the piezoresistor so that the maximum delta R we can achieve. The strain gauges are made from the doped silicon. Change in strain can be related to the applied pressure, and typical pressure range to what we can measure using this, that is 0 to 1 megapascal, right? So this is the basic working principle of the piezoresistive type pressure sensors. Fine. Is it okay, or any doubts? right? So what we understand that depending on the orientations of the piezo resistors, the locations or the placement, so we have to put it in such a way so that when the pressures will be applied, so then if we use 4 strain gauge or this full bridge configuration, then 2 piezo resistors will be increasing their resistance, whereas the other 2 will be the decreasing case, so that we can connect it to the Wheatstone bridge in full bridge configuration and we will get larger Vout. Fine? Okay. Now, so here we are showing some sort of simulation analysis and the fabricated device image, right? So you understand that suppose I am a designer and I want to design a MEMS based pressure sensor, right? So what will be my first step? I have to design it. That means firstly I should have a target that for what applications I want to use the pressure sensor, right? Accordingly, I have to define what should be the range, what should be the sensitivity, resolutions, accuracy, bandwidth, and so many important factors we have to take into account. Accordingly, we have to choose that suppose using the diaphragm, if we want to design the pressure sensor, then to achieve that particular target specification, what should be the dimensions of my diaphragm, thickness, length, width, those are the things. Fine. So accordingly, I have to make the design in just hand calculation. By hand, we will have some rough sketch, draw the things, and try to analyze. Right. And obviously, since this MEMS fabrication process is quite complex and challenging process, and in each step there may be some minutely you have to carry out the processes. So suppose the process cannot be repeatedly done by trial and error method, right? Because suppose if I want to achieve this target specifications, then I will design my membrane in such a in a particular configurations, dimensions, then we will design it, fabricate it, test it, and after testing, if we understand that there are wide deviations between our target specification and the actual specifications, then it will not serve the purpose, right? So that's why this fabrication process we cannot do it iteratively. Rather, to reduce the complexities or the costs involved or the labor during basically the efforts during the fabrication process, what we can do, instead of going into the actual fabrication, before that we do some sort of simulation and analysis, right? Once we are satisfied with the simulation or the analysis, then we will go for the fabrications for that particular dimension, right? So that's why for simulating the MEMS device, we have certain dedicated software tools like Coventorware, COMSOL. So these are some of the tools. And here, suppose for the pressure sensors, what we have to do, that due to a particular amount of pressure, what would be the typical stress distribution, accordingly how much resistance change we can get, accordingly how much voltage it can be generated. So likewise, these are the different factors. So that type of, just for the representative purpose we have shown. So suppose now generally these type of simulation tools, they are based on the FEM or finite element method analysis, and to do that we have to mesh it, right? So mesh it means discretize it in very small components, then we have to do the analysis. So here some sort of analysis simulation like if for a particular amount of force, what should be the stress distributions. So by the color map it has been pointed out here. Here is again another type of diaphragms where we have just now in the previous slides what we have shown, that 4 piezo resistors we are putting or mounting over here, and when the pressure is applied at the middle, then how the resistance change of those resistors will be there. So those things we simulate it, and simulation we can do multiple times, right? Because that will not take large cost. That will just, that is the computer job, so that anytime we can do some changing and accordingly the output change will be reflected. So these are some of the simulations, and at the below portions you can see some of the fabricated structures which are MEMS based pressure sensors. So here is some circular diaphragm is there, and here just we have shown suppose 2 strain gauges or piezo resistors are there like in this configuration, whereas in this case we can see 4 connections are there. So to take out the connections for the 4 piezo resistors which are connected at these 4 sides of this membrane, right? And these are the bond pads where from which will be basically connected to the Wheatstone bridge, right? So this is one terminal, this is another, this is another, this is another. So these correspond to the 4 terminals of the 4 strain gauge, and that can be basically directly connected to the Wheatstone bridge. right? So this is just to give you the idea about the simulation, analysis and fabrication, right? Now next one is that we have to go for this signal conditioning circuits as well. So as we told that if we go for this piezo-resistive type pressure sensor, then Wheatstone bridge is one important example which we can use for this converting this delta R into the delta V, right? And you can see that suppose this is your diaphragm, and on the diaphragm this R1, R2, R3, R4, these are the 4 piezo resistors placed, right? So when if we consider at the middle we are applying some compressive pressure, so then R1 and R3, what will happen? So R1 and R3, they will be elongated along their length, so R1 and R3 value will be increased, whereas R2 and R4 will be elongated along their width, so their value will be decreased, right? And so basically as we said, the strain gauges are made from doped silicon and designed in pairs with a readout circuit like Wheatstone bridge. Now suppose, so initially if the resistance was suppose R0, so then what will happen? The R1 and R3, their resistance will increase like plus delta R, here also plus delta R, whereas for R2 and R4 they will be minus delta R and minus delta R, and this is the full bridge configurations. And if we just consider this is the bridge configurations if they are connected in this particular fashion, so where across these two terminals we are applying the supplied voltage, whereas across these two terminals we are taking the voltage output, and if we analyze the voltage output will be getting in terms of Vs into delta R by R, right? So these derivations previously also we have seen when we have discussed about the different type of sensors, right? So thus this voltage what we will be getting, that is a function of the delta R, and delta R was a function of what? Delta P. Because why delta R was changed? Because we were applying some pressure delta P, and because of the delta P pressure the delta R was changing, right? Because these are the piezo resistors, delta R was changing, and that delta R we are converting it into the electrical output with the help of the Wheatstone bridge circuit, right? Is it okay? Is it convincing or any doubts? Yeah. So okay, so if you don't, let us look at the next slides where the further that modified or improved signal conditioning circuits are shown here. So as you can see that suppose these R1, R2, R3, R4, these will form the basic Wheatstone bridge circuit. Now here we have one op-amp based circuits, that is for which purpose? Because op-amp means that will essentially it can give you some sort of amplified voltage as well. Because suppose if your that applied pressure is very less amount, then the delta R will be also less. Accordingly, the delta V will be also less. But the delta V has to be in some measurable range, right? Because ultimately that voltage output, that analog voltage, we have to feed it to the microcontroller with the help of some ADC, right? Because mostly we will be dealing with the embedded controller or the microcontroller, right? So that's why to make it in sufficient high level we need some sort of amplifications as well. And here you can see, here we have shown one op-amp based circuits, which is here these are the two buffers and this is the differential amplifier. So basically this is your like your that if you remember that instrumentation amplifier we have talked about. So there is some sort of similar to that, not exactly like that, but it essentially includes two buffers. So buffers are basically for the to avoid the loading effect, and then the buffer output goes to the differential amplifier, and this V output, that V output is directly that will give you this delta V, right? And depending on this Rin and Rf, by adjusting this Rin and Rf, we can achieve specific amount of amplification as well, right? And this is one example of the op-amp based signal conditioning circuits, whereas the lower one is the MOSFET based signal conditioning circuits, where the microfabrication process or the technology has been used to develop both this MEMS sensors as well as the signal conditioning circuits both in a same wafer, right? If we can fabricate them in same wafer, then what type of technology we call it? Do you remember during when we started our microsystem basic introductory slides? We have, if you remember, we told that there are three types of integration. One is the hybrid integration, another was that monolithic integration, right? And another was the PCB integration, fine? So this particular thing, where the in a same wafer both the MEMS sensor as well as the circuits will be implemented or the fabricated, so then that particular type of integration we will be calling as the monolithic integration, right? And here is the example. So here suppose this is your bridge circuit, and this bridge circuit output, instead of connecting to the op-amp circuit, here we are just using some simplifying this MOSFET based differential amplifier configuration, and this MOSFET output will be that here is the V output, that is the delta V, which is a function of delta R, and that delta R was a function of delta P. So from this V out we can tell what is my applied pressure. And here is the fabrication technology has been shown here. So here what you can see, that this is our total silicon wafer, and in the left side this particular portion here, this bottom portion, so this corresponds to the silicon membrane. So this is your sensor part, whereas in the right side if you see drain, source, drain, gate oxide, metal, so those correspond to what? Those correspond to the MOSFET. So MOSFET full form is metal oxide semiconductor field effect transistor, right? And in field effect transistors we have typically three terminals. We have that source, gate and drain. So basically in this same wafer, in this side we have the MEMS, that is the sensor part, and this side we have the circuit part. So in the same wafer or the IC we have fabricated both that MEMS sensor as well as the circuit. And if we can do that, so then it will be the monolithic integration type of thing, and internally the MEMS as well as the sensor as well as the circuit has to be connected together, and finally we will get the output, right? So this is just to give you the idea that okay, so once we realize the MEMS pressure sensor using for that we have fabricated the diaphragm using our micromachining technology, and we can do separately as well. That separately we can fabricate the MEMS sensor, separately we can fabricate the IC or the signal conditioning circuits, then we can integrate them on the PCB. That is also possible, but in this case just one example we have shown where in the same wafer both the VLSI technology as well as the MEMS technology has been implemented together to realize or fabricate both the sensors as well as the circuits. Fine? Okay. So let us look at the next one. So far we have talked about the piezo-resistive type pressure sensor. So now next we will discuss about the capacitive type pressure sensor. Fine? So in that regard, let us first talk about that what is the typical working principles. Fine? So as you remember, that capacitive pressure sensor means when we will be applying the pressure on the diaphragm, so then that on the diaphragm we will deposit some sort of metal electrode, and above that we have some reference frame, and on that frame also we have some electrodes, and when the particular force will be applied, this diaphragms will be moving, so then the gap between this fixed frame and this diaphragm will change, and that gap will be calibrated or measured in terms of the capacitance value, right? Again, to convert the capacitance into voltage we need some signal conditioning circuits like bridge circuits or some other ICs which can convert the delta C into the delta V, right? So here as the discussion you can see, a capacitive bridge can be formed with two reference capacitors, and the output voltage is related to the deflection of the membrane delta X, and hence the applied pressure delta P. So basically the V output, that is a function of delta C, again the delta C is a function of delta X, and again the delta X is a function of delta P, right? So if you look at from this side, we are applying some pressure delta P, and because of the delta P some deflections of the membrane will happen, that is the delta X. The delta X we are measuring in terms of the capacitance, right? So converted into capacitance, then that capacitance has been converted into voltage with the help of the circuits, right? So this is about the basics of the capacitive pressure sensor, and accurate positioning of the pickup electrode is very crucial, right? Because if there is some misalignment of these electrodes misalignment, so then overlap area will change, accordingly it will change the capacitance value as well, right? Okay. Now here we have shown some comparison between the capacitive type and piezo-resistive type pressure sensors, right? So if you just see that, first let us talk about the capacitive type pressure sensor. So let us look see from the last in first out, right? So yeah, so capacitive we are starting with the capacitive, that comparison, right? So what are the advantages of capacitive, right? So if you see that in case of capacitive, the advantages are it is more sensitive, right? Because a small gap change that will lead to the larger capacitance change, and it is less temperature sensitive because it deals with the capacitance measurement, and capacitance measurement is almost less affected by the temperature, right? Okay. The next one is the robustness. So these are the three advantages of the capacitive sensors. So one is the sensitivity, another is due to the temperature it will not be affected so much, and its robustness is also more. Whereas if we go for the disadvantage, then capacitive type are mostly this large piece of silicon for bulk micromachining is used, that will lead to the cost, that is basically in terms of cost as well as the material point of view. Then electronically the circuits are bit complicated with respect to the resistive one. We need some integrated electronic circuits, and the main is it is affected, the parasitic or stray capacitance effect will be there, right? So this is the relative advantage and disadvantage of the capacitive type pressure sensors. Now if we look at the piezo-resistive type pressure sensors, so then what are the advantages of piezo-resistive? We can see this is smaller structure than the bulk capacitance, because the small piezo-resistors we have to just dope it. Then the transducer circuit is simple Wheatstone bridge circuit is sufficient, whereas in case of capacitance that simple Wheatstone bridge will not suffice. So we need some dedicated that capacitance conversion circuit which will avoid the effect of the parasitic as well. Fine. And another advantage is that integration may not be required, right? Because in case of capacitive sense, there the stray capacitance effect is high, so that's why the integration is highly important. Whereas in this case, that direct integrations may not be there. You can use some sort of hybrid packaging as well, or externally separately also you can connect the sensors and the circuits together, right? Now if we look at the disadvantage, this is the major disadvantage of the piezo-resistive. It is highly temperature dependent, right? Because we know that resistance change not only depends on the strain, but it is a very important factor. Temperature is a very important factor, right? So because of the temperature, the resistance will change. So you cannot identify whether the change is because of the applied pressure or the applied temperature, right? So environmental temperature. So that's why, but still we have told previously also that if we use some full bridge configuration, then the temperature sensitivity we can reduce, right? Okay. And another important factor is that disadvantage is that piezo coefficient depends on the doping level. So these are the relative advantages and disadvantages of that capacitive and piezo-resistive type pressure sensors. Fine. So with this we have talked about the pressure sensors in details, and under which mainly two types of transduction mechanisms we have talked about. One is the piezo-resistive type, and the capacitive type. So the summary is that in the piezo-resistive case, because of the applied pressure, what happens here, we use some sort of doped polysilicon resistor which will act as the piezo-resistor, whose resistance will change depending on the applied strain or stress or the pressure. Fine. And that resistance change we are converting into the voltage, and that voltage will be the function of the applied pressure. So that is the piezo-resistive type. Whereas for the capacitive type, we have to use some electrodes on the diaphragm as well as above the diaphragm on the reference frame, and when the deflections of the diaphragm will happen, the capacitance will change, which will be measured in terms of that means that will be converted into voltage, and that voltage will be actually a function of the delta P. Right? So is it okay? Any doubts about the MEMS based pressure sensors? Okay. If you don't have any doubts, so then we will go for the next type of pressure sensors. They are also mechanical types, and they are mostly called as the inertial sensors, and under which the two popular things which is known as the accelerometer and gyroscope, right? Okay. So if we look at the pressure sensor, just now what we have finished our discussion, the pressure sensor is the largest volume. So pressure sensor, the production point of view, use point of view, pressure sensor comes in rank 1, and the accelerometer will come in rank 2, right? In terms of its large shelf volume, right? Okay. So most important type of mechanical microsensors is inertial sensors, as we told, and for measurement of the acceleration as well as the angular velocity. And these inertial sensors are basically of two types. One is the accelerometer and another is the gyroscopes, right? So next our topic of discussion is the accelerometer and the gyroscope, fine. And as just now what we mentioned, that the micro accelerometer has the second largest sales volume after pressure sensor, and the gyroscope so basically this accelerometer mainly it is used to measure the linear acceleration in you can measure it in single axis or 3 axis or 2 axis, whatever, and gyroscope is mainly used for measuring the rate or angle of rotation, right? And it is also becoming popular gradually, and both of these inertial sensors have wide applications in automotive, robotics, consumer electronics, biomedical, and so on, fine. And here is some this is one fabricated accelerometer structures has been shown here, and this is another accelerometer. So this is here again this accelerometer also we will be discussing that two types. The one is the piezo-resistive accelerometer and another is the capacitive accelerometer. Like pressure sensors, we have discussed mainly the two transduction mechanisms, right? Piezo-resistive pressure sensor and capacitive pressure sensor. Similarly, for accelerometer also we will be discussing the piezo-resistive accelerometer and the capacitive accelerometer. And here is some of the figures that this is the piezo-resistive type, this is the capacitive type. So each of the things we will be discussing in details individually. Fine. And you remember these figures you have seen when we have shown that testing slide in the last class. During testing we have shown on this type of slides where the accelerometer data has been shown, right? So there we mentioned that this is the piezo-resistive accelerometer data, and when we have to test it, so test it means we have to see that whether our targeted specifications we can achieve or not with our fabricated device, right? So that thing we have to test. That means for accelerometer the input output characteristics we have to ensure. So input is what? In case of accelerometer the input is the acceleration and output will be the voltage typically, right? So actual output may be displacement, but that we have to convert it into voltage, right? So that is the thing. And here just for representation purpose we have shown this two diagrams. Okay, is it okay about the introduction of the inertial sensors? Yeah. Okay. So although you know, so just for the continuity purpose, here we have shown the mechanical model of an accelerometer, and you can essentially understand that accelerometers can be simply modeled with the help of a second order mass spring damper system. Is not it? So here this is the schematic of this mass spring damper system, where this one is the mass, this is the damper, this is the spring constant, and here is again another simplified view where this is your mass, and suppose with this mass some spring arrangement is there, and here we have some bottom electrode or top electrode, and when this will be moving, so then gap between the electrodes will change, and that can be converted in terms of the capacitance, just for example. So this is just the model, mechanical model, right? Now if we look at the structure, so basically the proof mass of mass A, that is suspended by a suspension beam. Suspension beams means this one, which is having the effective spring constant K, and this is anchored to this particular fixed frame F, right? And a damping factor D is also present, which affects the dynamic movement of the beam, right? So that can be because of the air friction or some other type of damping can be there, and this will try to prevent the motion, right? So this is the basic structure. Now what is the principle? So external acceleration displaces the support frame relative to the proof mass, which in turn changes the inertial stress in the suspension spring. Both the relative displacement and suspension beam stress can be used as a measure of acceleration. That is very beautiful principle. So what we told, that basically this is your accelerometer, and it will be obviously some reference frame will be there. So this will be the reference frame, and inside the reference frame your accelerometer is present. Now that particular reference frame you can think of as a complete package, and inside the package we have the accelerometer device, actual device, and that package we will place it on the platform which is having some sort of acceleration. Now when the acceleration or force will be applied, so then what will be happening? The reference frame will be moving, and this particular mass spring system is attached to the reference frame, So there will be relative motion between the reference frame as well as the displacement of this mass, right? And that relative displacement will be that depending on the applied acceleration, the relative displacement will change, and that displacement will be converting into the corresponding either the capacitance value or resistive value, and then that value we can finally convert it into voltage, so that the final output will be the voltage, right? So that is the basic principle. And if we talk about an accelerometer, so what are the different performance parameters? Like for example, we have seen that what are the typical parameters for a sensor. So like sensitivity, then range of the device, frequency response, that means how much frequency it can it will be working within how much frequency, the resolution, non-linearity, offset, shock survival capacity, and off-axis or cross-axis sensitivity, right? So these are some of the important parameters or features for an accelerometer device, right? So these are the just basic introduction of the accelerometer system, right? Is it okay? So here again we have shown, so this is our accelerometer model mass spring damper system. So when the force is applied, so then mass spring damper, all the things will be moving. So spring damping, resisting force due to weight, force downwards due to weight, spring stiffness, force upwards from the spring, direction of motion. So these are just indicated here, and this is the mass spring damper model, and this is one typical frequency response example, right? So here we can see that resonant frequency is somewhere here, and from here to here it is almost flat range. So that means the working range of the accelerometer can be typically in this region, fine? Now if you want to operate it in resonant frequency, so then you have to choose this one. Now whenever we have some mass spring damper system, so then this is the typical transfer functions, right? So x is the displacement and a is the acceleration, and this is the second order mass spring damper system transfer function. And the two important parameters, one is the undamped natural frequency, which can be given by root over k by m, where k is the stiffness and m is the mass of this proof mass. And another important factor is the damping ratio, that will again dictate you the dynamics of the system, which is again given by the lambda by 2 root kf, right? So lambda is the damping constant, k is the stiffness, m is the mass. Now here, just for your understanding or representative purpose, here one table we have shown where two applications we have considered. One is the automotive, another is the navigation, and for both the applications we are using an accelerometer. We want to use the accelerometer, right? Now depending on my applications, the parameter values will be different. So just to give you the idea, suppose if you see this automotive application, the range of the accelerometer should be plus minus 50 G for airbag or plus minus 2 G for vehicle stability. Whereas for navigation it will be typically plus minus 20 G. Similarly, resolution, that means what is the minimum change in input it can measure. So for automotive requirement is less than 100 milli-G for airbag or less than 10 mg for this vehicle stability. This G corresponds to the acceleration, right? So the acceleration is measured in terms of G. So 1 G means 9.8 meter per second square. Okay. Whereas in case of navigation, this resolution is very important. You can see this is less than 4 micro G. So that means 10 to the power minus 6. So that amount of resolution is required, right? Frequency range, if we see, it should work from DC to 400 Hz, whereas in case of navigation it is DC to 100 Hz. Similarly, these are the temperature range. These are the off-axis sensitivity. So off-axis means, suppose if I want to measure it in x-axis, then if I apply some y-axis acceleration, then it should not be affected, right? So that effect is given by the off-axis sensitivity, right? So here this requirement is less than 5%, here less than 0.01%. Then again we have this temperature sensitivity. Then again here we have the non-linearity requirement. So you can understand that navigation requires much more precise parameter values, right? So these are some of the typical specifications. So far we have talked about the MEMS pressure sensors in detail, piezo-resistive type, capacitive type, and then we have given the introductions of the MEMS accelerometer. And with this we are stopping here, and next class we will continue with the details of the MEMS accelerometer. So we will discuss about how the piezo-resistive accelerometer work, how the capacitive accelerometer work, what will be their typical signal conditioning circuits, etc. Fine? Okay.